far, we've been thinking only about objects moving along a straight line, back and forth along a straight line, and thinking about the net forces that could cause those objects to either speed up or slow down. Now we'll look at something a little bit different, circular motion. And to keep things relatively simple, just for the moment, we'll consider only uniform circular motion. By uniform, we mean the speed stays the same. But since it's circular motion, even though the speed is staying the same, the velocity is still changing. So there's still an acceleration. As an object moves along its circular path, the direction of its velocity changes. Or, in other words, the velocity changes, and that means acceleration. Imagine something moving along this circular path. At one point in time when it's near the top of the circle, it's here, and at any point along a curved path, at any moment, the actual direction of the thing's velocity is pointing along a straight line tangent to the curve. So the velocity right here, we'll call it an initial velocity, because this is when we imagine that we start watching the object when it's right here. There's the initial velocity, and then we wait a little bit longer so that it's just as far to the right of the top of the circle as it was to the left of the top, to the left over here. So nice and symmetric, and at that moment the velocity is again pointing along a line that's tangent to the curve at that point. So there's the final velocity at the end of our observation. And let's compare those initial and final velocities. They're different, so there must have been acceleration. Velocity changed from the initial moment to the final moment. And remember how we can think about velocity change. Think about it in terms of delta v, which is what you add to an earlier velocity in order to make the later velocity different. So here's the earlier initial velocity, here's the later final velocity, and I draw them with the same length because to indicate that their speeds, the magnitudes of those velocities, have not changed. So you add some extra velocity to the initial velocity in order to get the final velocity. So if you take this velocity and then add to it this velocity, you get this velocity. That's the usual pattern for showing how things, how vectors are added. Initial velocity vector and the delta v arrow are added, so you connect them tail to tip. The tip of vi is right at the tail of delta v, and then the net result of adding those two vectors is a path that took you from here to here, and the net result is just means you go from this point to this point. So an arrow that takes you right from the beginning to the end of the path, that's the sum, the net result of adding these two. Like the sum of v initial plus delta v is v final. And the important thing to note here, the delta v points down, and we were looking at a time interval where half of that time comes before the object is at the top of the circle, and the other half of that time is when the object is past the top of the circle. So the average velocity during that time interval is straight down. And our argument would work exactly the same way if we made this time interval smaller and smaller and smaller and smaller, just having the top of the circle centered on that smaller and smaller interval. Smaller and smaller, so that for all practical purposes now it's just a point right here at the top, but the delta v points the same way, straight straight down. And remember our definition of acceleration. That tells us that the direction of acceleration is the same as the direction of delta v. So if delta v pointed straight down, then the acceleration points straight down. Or, put it another way, it's pointing directly towards the center of the circle. Directly towards the center of the circle. And that result works exactly the same way if we choose any other pair of points for finding a v initial and then a v final and comparing them. Any two points that we choose on the circle, we'll always find that the delta v you get by comparing initial and final velocities will always point straight towards the center of the circle, which means that the acceleration is always pointing straight towards the center of the circle. And I use a subscript c here, which means centripetal. Centripetal meaning pointing towards the center, because this is the acceleration that always points toward the center of the circle. Whenever something is moving in a circular path, there will always be this kind of acceleration that points toward the center of the circle. Whenever something moves in a circular path, there is always this centripetal acceleration. Well, it's an acceleration, so it has to be caused by a net force. Acceleration in this direction must be caused by a net force in this direction. That's one thing that Newton's second law tells us. So when the moving thing is right up here, it's feeling a force pulling or pushing, pointing straight in towards the center. So this force would just be the net force along this line, along the line of a radius of the circle. So we can call it the net centripetal force because it's pointing in towards the center of the circle. Or for short, I'm just going to call it plain old Fc for centripetal. Fc, centripetal force, will always mean the net force pointing toward the center of a circular path. And there always is a force like that, a force pointing in towards the center of the, a net force pointing in towards the center of the circular path. If any time there is motion in a circle, there's always that centripetal force. Now, the important thing to note about centripetal force is that it is not a new type of force, like in the sense that weight or normal or friction or spring force are types of forces. Centripetal force is simply one or more of the forces that we already know about, weight, tension, normal force, friction, whatever. It's just one or more of those forces that we already know about acting in a particular kind of way, acting in a different kind of way, acting so as to cause a centripetal acceleration. In other words, to cause circular motion. For example, imagine a planet revolving around a star. If it's moving in a path like that, approximately a circular path, there must be some kind of centripetal force that's causing the planet to move in that circular path. And in this particular case, the force that supplies the centripetal force is the gravitational force from the star on the planet. Another example, say you're driving down the street and you're going to make a right turn, and here's the view of you as seen from above. You make the right turn like this. While you're turning, you're moving in a curved path that we can say is pretty close to circular. So if you have circular motion, there must be a centripetal force that's making you move in a circular path. What is that centripetal force? Well, if you weren't able to move in a nice circular path, like for instance, if it was a very, very icy road, you would slide away from that path. But you're not sliding. You're sticking to the path. And remember, if sliding is prevented, it is prevented by static friction. So the force that keeps pushing you into the circular path, the force that prevents you from sliding away from that path, is static friction. Static friction is supplying the centripetal force in that case. Or one more example here. So this little plug on the end of this wire, and if I'm spinning the plug around in a horizontal plane, as seen from above, the plug is rotating in a circle. What's the force that supplies the centripetal force in that case? Well, it's the tension in the wire, pulling in towards the center of the circular path, pointing towards the center of the circular path the way any centripetal force should. And that's what causes the circular motion. Now imagine one slightly more complicated version of this. Spinning the plug in a vertical plane instead of a horizontal plane. Now there's another force that we have to take into account, weight. And in this case, the centripetal force that makes the plug spin in the circular path is a net force, a combination of both the tension and the weight. Let's see how that works. All right, in this case, there's the path of the plug in a vertical plane. And let's say right here, when the plug is right at the top of the path, top of the circle, the two forces acting on it are, of course, weight and, well, let's look at here at the bottom first. At the bottom, there are, of course, two forces. There's tension and there's weight. Weight always pulls down. Magnitude of weight is mass times gravitational acceleration. And then the tension is always pulling in towards the center of the circular path. So the tension is like that. Since the plug is moving in a circular path, we know there must be a centripetal force. In other words, there is a net force along a radius line like this. There must be a net force along a radius line pointing in towards the center of the circle. The combination of the tension and the weight must be a centripetal force. In other words, must be pointing in towards the center of the circle. So when we write down our expression that shows how forces combine to give the net force, of course, we need to do that. We need to know what's the positive direction, what's the negative direction. Whenever we have a centripetal force case, we always make the positive direction the direction in towards the center. So that's the positive direction. Away from the center is the negative direction. And so the net force, when the plug is here, is all the force in the positive direction minus all the force in the negative direction. But since it is moving in a circle, we know that there must be a net force pointing in towards the center. In other words, we know that the net force is pointing this way in towards the center, which is the positive direction. In other words, the net force is positive. That difference between T minus W is positive, which means at this particular moment the tension in the in the wire is actually stronger than the weight of the plug. And then let's think about what happens now at the top of the circle. At the top of the circle, the forces on the plug are still the same two forces, weight, which always pulls down, and then tension, which always pulls toward the center of the circle. So at that moment, it's also pulling down. And since it's moving in a circle, we know there is a centripetal force, that is the net force along a radial line, and it points in towards the center of the circle. So there must be a net force in this direction, and obviously there is, because both these forces are pointing in that direction in towards the center of the circle. And if we always say that towards the center of the circle is the positive direction, away from the center of the circle is the negative direction, then in that case, the net force, which is of course the centripetal force, the net force along this line is the centripetal force, is just all the force in the positive direction, which is weight plus normal in this case, or sorry, weight plus tension. Instead of weight minus tension. Okay, just a couple simple examples. Now, like any net force, the centripetal force causes acceleration in the same direction, and since this acceleration is caused by a centripetal force, we call it a centripetal acceleration. And we actually have a nice rule for calculating the magnitude of centripetal accelerations. It looks like this. The magnitude of a centripetal acceleration is just speed squared divided by radius of the circular path. It's not important to know where this equation came from, but one does need to be able to understand, first of all, why the equation looks that way. For example, why is it that a bigger speed would correspond to a bigger, stronger centripetal acceleration? Well, think of it this way. Compare two different situations. You've got a mass moving in a circular path at one speed, and then moving in the same circular path, same radius. Make it actually look sort of like the same radius. At a different speed, let's say that speed 2 is greater than speed 1. So the magnitude of velocity 2 is greater than the magnitude of velocity 1. Right? Remember, this is just the meters per second as the object moves through this path. Well, now let's compare how far the mass goes in a certain amount of time this way, compare it to how far the mass goes in that same amount of time under these conditions. So we'll start watching the mass when it's right here, right at the top of the circle. And of course, at that moment, its initial velocity is like that, pointing along a straight line that's tangent to the curve. And let's say we watch long enough so that by the end of our time interval, it's gone through 90 degrees. It's gone through 1/4 of this circle. So at the end of our observation, it's right there. So at that moment, the velocity points straight down. Final velocity is represented by an arrow like that. And I want those two arrows to be roughly the same length to indicate that the magnitude of those velocities did not change. The speed is the same all the way around the circle. Now, think about the same kind of thing. Again, we start observing when the mass is right there. We watch the mass for the same length of time, but now the mass has a higher speed. So it'll start out right here, but with a higher speed. So I'll indicate that with a longer arrow. So there's the arrow that represents initial velocity. But now, since it's going at a higher speed, and we're watching it for the same length of time, it'll go farther around the circle than this one did in the same amount of time. So let's say instead of getting this far in that amount of time, it goes this far in that amount of time. So the final velocity would look like that. Now, let's compare the change in velocity between this situation and this situation. Situation 1 and situation 2. So delta anything is the final value minus the initial value of the thing. So initial value plus delta is the final value, like we always say. Delta V is the velocity that you add to an earlier velocity in order to get a different velocity when the object is accelerating. So let's compare the initial and final velocities to see what delta V has to be like in situation 1. Initial velocity like this, situation 1, and final velocity like that, same same length, but pointing at a 90-degree angle now. So what kind of extra velocity do you have to add to this in order to get this? Well, it would be a velocity like this. You're adding delta V to VI, so you put the tail of delta V at the tip of VI. And then that makes a path that started here and ended here. So the net result of adding this to this is to take you from here right to here. The net result of VI plus delta V is the sum, which we call V final. V final is like that, and you had that kind of a delta V in order to make that kind of a delta V added on in order to make VI change into V final. Now let's look at situation 2. In situation 2, we again start out with the initial velocity horizontal pointing straight to the right, but now it's a higher speed, so a longer arrow. And by the time it's all over, the final velocity is pointing like this. Same length indicating no change in speed, but just a different direction. So again, what did you have to add to this initial velocity in order to get a final velocity like this? The extra velocity added on to V initial. The delta V is like that. You're adding delta V to VI, so you connect the tail of delta V to the tip of VI. And that gives you a path like that, which takes you from there to there. So the net result is taking you from there to there. the net result, the sum of VI plus delta V, is represented by that arrow for the V final. And notice one thing pretty obvious in these drawings. The magnitude of delta V2 is bigger than the magnitude of delta V1. And remember our definition of acceleration. Acceleration is change in velocity divided by the length of time you spent watching that change. Well, whether we're talking about situation 1 or situation 2, the time you spent watching is the same. So the only thing that would make acceleration different in situations 1 and 2 would be delta V being different. Since delta V is bigger, has a bigger magnitude for situation 2, then acceleration 2 has a bigger magnitude. Centripetal acceleration in situation 2 has a bigger magnitude than centripetal acceleration in situation 1. Now remember what centripetal acceleration means. It's an acceleration that you have when an object's velocity is changing direction. So what centripetal acceleration tells you is the rate at which the direction of velocity is changing. How fast the direction of the velocity is changing, as opposed to how fast the speed is changing. And since the direction of velocity changed from this to this in situation 1, and you had a much bigger change in direction in situation 2, then you had more change in velocity in that same amount of time in situation 2 than in situation 1. More change in the same amount of time means bigger acceleration. And that's why it makes sense that magnitude of centripetal acceleration is related to higher speed. Higher speed means larger magnitude of centripetal acceleration because higher speed means more change in the direction of velocity. More change per second in the direction of velocity. Lower speed meant less change per second in the direction of velocity. The direction of velocity changed faster when the speed is higher, simply because you're going around that circular path faster. Now, one other thing we should say about magnitude of centripetal acceleration. I'll go back to the simple case where I'm spinning the plug in a horizontal path. So tension in the wire is supplying the centripetal force. Centripetal force is the tension in that case. Centripetal force, remember, is the net force along a radius line. This tension then entirely supplies the centripetal force, the net force along this line. So that's a net force, which means it's equal to mass times acceleration. It's causing a centripetal acceleration, so this is mass times centripetal acceleration. And the magnitude of centripetal acceleration is just v squared over r. Now imagine I keep the plug moving in the same circle with the same radius. R does not change, but I adjust things so that I make the plug spin faster. So that's constant, but speed is changing. So I've got this equation here, mv squared over r but M and R are constants. So I could write the equation like that, and this equation, tension equals this constant factor of M over R times this variable factor V squared, looks like this. Some variable equals a constant times another variable. That's the general pattern for direct proportionality. And that's important because we can say something about how things change when there's direct proportionality. We can say something about how a change in one variable affects the other variable when there is direct proportionality. In this case, the y variable corresponds to tension. The constant factor corresponds to mass over radius. And this, what this says is that in the term that has the other variable, x, everything that isn't constant is the variable. Here's all the constants. Here's everything else. Here's everything that isn't constant. Everything that isn't constant is v times v, two factors of v. Everything that isn't constant is v squared, not just v. X corresponds to v squared. So the two variables that are proportional to each other are tension and speed squared, not speed. And you write it like this: tension is proportional to, remember this is the symbol that is read as is proportional to v squared. And we've worked a little bit in class with the principle of inverse proportionality. Here, it's a very similar principle, the principle of direct proportionality, and it goes like this: when one of the proportional variables changes by some factor, that's when you have direct proportionality. That is, if one variable is just has that kind of a relationship to the other, and one variable changes by some factor, that is, the new value is just some factor times the old value, then the other variable changes exactly the same way. y2 changes by exactly the same factor. For example, if we have an equation like this, y equals 10 times x, if x is 1, then y is 10. But if x doubles, then y is now 20. In other words, y also doubled. When this variable changed by a factor of 2, the other variable that it's proportional to changed by the same factor. And that's how direct proportionality works. So in this case, let's say we've got a situation like this. When you have one particular tension in that wire of, let's say, 10 newtons, that produces one particular speed. Now I increase the tension enough to double the speed. That is, the new speed is twice the old speed. Speed changed by a factor of 2. But I know that tension is directly proportional to speed squared. So, however this variable changes by the same factor. That's what it means for those two things to be proportional to each other. So, it's not enough to know how speed itself changes. I need to know the factor by which speed squared changes. and then because of the proportionality, tension will change by the same factor. Well, you can figure out how speed squared changes really easily just from this equation. Just square the whole equation. So on the left-hand side now we have the new value of v squared, and square everything on the right, 4 and v1 squared. In other words, the new value of v squared is 4 times the old value of v squared. This variable called v squared changed by a factor of 4, which means that whatever it's proportional to, tension in this case, also changes by a factor of 4. New tension is same factor times old tension. The old tension was 10 newtons, so now it's 40 newtons. There's a tendency, even when you know better, to jump to a conclusion in a situation like this. You see this 2, so you're thinking about doubling, and it's very easy to jump to the conclusion, speed doubled, therefore tension must double. No, because you can't say that, because speed is not related in a proportional way to tension. Speed squared was related in a proportional way. You had to go through these steps in order to get to the correct answer. The tension increased by a factor of 4, it didn't double. Okay, that is just about everything you need to know about centripetal acceleration, but as always, figuring out how it applies in all kinds of different situations gets kind of tricky sometimes. We'll practice that in class.